Right, the next thing that we very often do then is we would plot graphs for our motion, or for the motion that's going on. And the first type of graph here, and the simplest type of graph, is a distance time graph. So this is showing a distance time graph for a car. And someone has recorded the distances a car has travelled every second for a total of 55 seconds. And these have all been plotted onto this graph. So you can see the motion of the cars changing, and you can see the distance it travels during each second isn't the same because that's increasing. So the total distance travelled there is obviously a distance of 1,000 metres. So you can just read that directly off the graph. Now, how the motion is changing in each part of the graph is slightly different. You can see there in the first part of the graph, how the graph is changing is different in each case. You can see in the first part of the graph that the distance travelled is very little in the first few seconds. And so we are saying there that the car is actually starting to accelerate because there's a slope in the graph. So that would make sense if you're starting from rest. The distance that you travel obviously is going to start increasing and increasing if you're accelerating. The next part of the graph is a nice steady line here, and that means for every further second the car is travelling that it's passing the same or moving the same distance. So we say that it's travelling at a constant speed. In this part of the graph then, the distance being travelled in each second is getting less and less. So instead of accelerating, we're saying it's decelerating. And in the last part of the graph, you can see there that it's completely flat. That means it hasn't travelled any further distance as it went on from, say, about 47 seconds there. As time went on, no further distance. So in this part of the graph, the car is at rest. So the total distance travelled there is 1,000 metres. And if you were asked to calculate the speed of the car, or the average speed of the car, you would take the total distance and divide it by the total time to get your answer. Now, we said in the middle of that graph there, in the last graph, that there was a very constant sloping line. And if you have a graph with a sloping line like that, you can calculate its gradient. And the gradient of a distance time graph gives you its speed. So if we needed to get speed from this graph, we would calculate the gradient of the graph. Now, if you can see the red lines here, there's a red line drawn here, and then there's red lines drawn here. This is giving you a triangle, and we use a wee triangle to calculate a gradient. And so the triangle here, you have to find the change in the y over the change in the x-axis. Or in physics, what we say, to get the gradient of a graph, you're getting the rise over the run. So the rise is the upwards part, and the run is the across bit. Sometimes, be careful, sometimes the graph goes down the way. So rather than rise, it's a fall, and then it has a minus value. So in this case, the rise goes from 200 up to 800, so it's a difference of 600 metres. And the run is from 15 up to 35, no sorry, it's a bit more than 35, 37 seconds. In fact, it isn't 15, it's about 17 seconds up to 37 seconds. So that's a total of 20 seconds. And 20 goes into 60 30 times. And so the answer is 30 metres per second. So that's how you find the gradient of a graph. A good big triangle. If your graph starts at the origin and it's a lovely straight line, just take your triangle right down to the bottom axis there, and a really good big triangle. And that gets you that answer. Now, can I just show you, if I go back here a minute, this was a distance time graph. This would work exactly the same way for a displacement time graph. So if this was a displacement time graph, then what you would be getting here, instead of a constant speed, you would be saying it was a constant velocity. You could, on a displacement time graph, have negative values. You won't have on a distance time graph. So a displacement time graph with negative values will indicate that the displacement's actually in the opposite direction. So if it goes beneath the axis here, then it's in the opposite direction. And similar for this as well. If it was a displacement time graph, instead of the gradient of the distance time graph giving us speed, the gradient of a displacement time graph would be giving us velocity. And again, that graph could go beneath the x-axis and those values could be negative. Okay, this graph shows us a speed time graph for a car, and what you might be asked to do is describe what the motion of the car is. So in this case it's a speed time graph, and we have to have a wee look at what's happening with the speed. So what's happening with the speed here? The speed is increasing. It's not a constant increase. Okay, so if the speed's increasing, it's accelerating, but it's not constant because it isn't a straight line. So all in this part here, there's an acceleration going on. In this part of the graph here, you can see that the speed is staying at a constant value over this period of time, and so you're going to say that it's moving at a constant speed. Again, this could be velocity. You could be changing that to velocity. And in this part of the graph here, you can see that the line is going right down to 0. So its speed is going from 30 right down to 0. So it must be decelerating. And in this case, that line is perfectly straight. So for every further 5 seconds the car travels, it is decreasing its speed by an equal amount. So we say that it's a constant deceleration. And if you had to calculate the gradient of that part of the graph, you would get a negative value. And so the gradient of that part of the graph would give you a deceleration, and it would be constant. So just to write down just about the gradients here, this is a non-uniform gradient, or non-constant. And that gives you an acceleration. This is a gradient of 0. It isn't changing at all. So you just read the speed of the graph or the velocity. So the speed in this case is 30 meters per second. In this case, we have a constant deceleration because it's a nice straight line. And to get the deceleration, we calculate the gradient of the graph. And if we just do that, you can see there that you have, if I just go down there, that's going from about, we'll just say it's 35 seconds there. So it's going, the rise, or in this case it's a fall, the rise is 30. I'm going to put a minus in because we know it is decelerating, it should be a minus value. And then the run there is from 35 to 50, which is 15. So that part of the graph has a constant deceleration of -2, and deceleration is measured in meters per second squared.